Well, I'm really happy to have GOTO Chicago back in town. I hope you'll tell your friends and bring out, double the crowd next year. It's really, I think, kind of the best conference we have in town. So, except for this talk, of course, but other than that, also, if you want to heckle at any time or ask questions for clarification, the door's that way. No, feel free to do that. So, yeah, I've been at IBM Research the last year, and I actually, recently my team got pulled into the sort of large language model work that they're doing, like everybody's doing right now after ChatGPT came out. So it's been an interesting ride, but I've been interested in reinforcement learning for a while. In fact, I have kind of a funny story about it. So it was kind of this obscure part of machine learning, maybe a decade ago. Everyone had at the time was thinking about supervised learning and unsupervised learning. And if you're not sure what those are, I'll describe them briefly. And then there was this sort of oddball, ugly duck called reinforcement learning that people would talk about, quietly amongst their friends because, it wasn't kind of socially acceptable, I guess. But I was actually reading the one textbook about it at the time. And then there was this big announcement from DeepMind how they were achieving expert gameplay in things like Atari games with this thing, reinforcement learning, that nobody paid attention to. And it has actually proven to be very useful for that. And in interesting ways, it's being applied to other things like ChatGPT and other large language models. And we'll talk a little bit about that. By the way, the photos are from Wyoming. I always put in photos from backpacking trips or whatever. So if you're bored with the content, you have something pretty to look at least. All right, so we'll cover these topics. What is reinforcement learning? How does it work? How is it used? Why is it important? A little bit about one of the toolkits I worked with before, which is RLlib. Ray is this really hot framework in the Python world, distributed Python world. I actually worked for a little while for the startup doing Ray called Anyscale. If you're doing distributed Python, it's something you should probably learn just because it's so useful, but it's really easy to use, relatively speaking. We'll dive into a little bit of some of the interesting challenges with reinforcement learning, and then we'll dive into a bit about how it's used in ChatGPT, and also how it's being used now for ad serving and recommendations, which on the surface, as we discuss what this is all about, you wonder, well, where's the connection? But there's actually some interesting connections between reinforcement learning and these ideas that we've actually been doing for a while, namely, serving ads and doing recommendations. And then I'll have some follow-up stuff. By the way, the slides will be available through the conference, and I actually have twice as many slides, most of which are in the extra stuff. So definitely download them to learn more and get more stuff. So very briefly, here's what it's all about, and then I'm going to show you a cool video that shows it in action. The idea is that you have some environment and some agent. It could be multiple agents, but for simplicity, one agent is interacting with that environment. And basically, that agent decides to do something, take an action that it can do, step forward or sideways, whatever. And then it observes how the state of the environment changed and whatever reward it might have received, like it picked up magic or something. There's not always going to be a reward at the end of each step, but sometimes there is, and we'll get into that a little bit later. And all along, so what happens is the agent is going to do this over and over and over and over again, repeating this process of dying or whatever until it finally stumbles upon good things, and it's trying to develop a policy for how it should interact with the world to maximize its reward cumulatively. So, in fact, one of the challenges is not to over-optimize for temporary rewards or short-term rewards, but globally, what's the best? And just to finish out some terminology, when you do this sequence of play from start to finish of a game or whatever, it's called an episode, and we'll talk about millions and millions of episodes and so forth. By the way, there's seats up front if you want to get called on, but feel free to. Anyway, and as I said, sometimes you get a reward after each step, sometimes you don't. And that actually proves very interesting because you're trying to figure out how do I maximize for a reward. All right, so just for motivation, here's a great video. I'm only going to play about 4 minutes of it, but I just love this video because it shows some of the cool things that happen in a reinforcement learning environment. And this is a project from OpenAI, by the way. Let's see if this will play. All right, let me stop there. Yeah, notice the numbers. It was like millions and hundreds of millions, billions kind of thing. But it was, and that's the way this is often done. You start with these incredibly
In this series, my mission is to showcase.
There we go. You start with these incredible, kind of naive things where it's just random pandemonium, and then it slowly just stumbles upon what actually works. And we'll come back to a problem of, well, maybe that's not so great if it's stumbling around and you're trying to train something to run a chemical factory. You really don't want it stumbling around while it's running the chemical factory until it learns. But there are techniques for getting around that too. So let's go back to the slides here. So how does this compare to supervised and unsupervised learning? Well, in supervised learning, you start with labeled data, like for some vector of features X, there's a Y, like the price of a house or whatever, and you train a model so that when it sees similar data, it predicts the Y values to be in a similar way. So that's supervised learning, probably one that all of you may have at least learned about if you haven't actually used it at work. And then unsupervised is normally about things like I've got this data that doesn't have any labels, but I'm trying to find structure in it, like clusters of things or graph relationships or whatever. But this is different. It's actually really most useful for sequential problems, like gameplay or anything where I have a sequence of things happening, I have evolving state. That's where reinforcement learning is especially useful. So just quickly, here's some of the examples. So I mentioned this at the beginning that it was about 10 years ago when DeepMind, this group within Google, announced that they had developed expert-level gameplay by using reinforcement learning, pretty much in kind of the way we just saw. And actually, just looking at the pixels on the screen for an Atari game, they could actually develop expert-level play. And then they really shocked everybody by actually achieving the world's best abilities at playing the game of Go. And the reason Go was interesting was that the state space, the number of possible moves and all that is actually much, much bigger than chess. Chess had already been done by this point, but to actually do Go was kind of phenomenal. And I'll come back a little bit in a few minutes to the architecture of what was going on behind the scenes, which is kind of interesting. As you can imagine, there's a neural network involved, like in everything. Obviously, robotics, autonomous vehicles, robots in general, things like that are typically kind of autonomous, navigating a maze, learning how to sort books, that kind of stuff. It's been used in industrial processes. So here's a state-of-the-art assembly line, which you'll appreciate. There's a lot of times where you need to optimize how they work, like supply chain things, how things get into the assembly line, how to do an assembly of a complex project. System optimization, there was a paper out of Google some years ago where they were talking about optimizing their HVAC systems using reinforcement learning. Advertising and recommendations, and this is not one you'd think of offhand as being like, well, how's that sequential? Well, what's sequential is the fact that your preferences change. And the current models of doing adjacency matrices and whatnot don't really account for how your preferences evolve. We'll come back and look at this a little bit later. And then, of course, finance. Anything new has to be tried in finance, and it is very much a good candidate because of its sequential nature. And then, so common theme, but then also it's being used in kind of an interesting way in ChatGPT. Again, this may not seem like it's too sequential, but yet text is a sequential thing, and the kind of interactions you have with a chatbot are also sequential. So there's both an aspect of you correcting its mistakes and getting better answers, but there was also techniques that they used that Alex talked a little bit about yesterday, and we'll come back to, where they're using it with human feedback to actually improve the quality of the results. All right, so here's the AlphaGo example and what the neural network looked like. And kind of the key thing here is, in this case, the observations were the board state. That kind of makes sense. Where are we on the board? Actions would be, where do I place the next stones? And in this example, there is no reward until the very end. Either you won or you lost. So the reward doesn't help you much in intermediate results. But as they looked at the neural network, what they found was that these sort of neurons and groups of neurons were finding increasingly large structures that apparently are important in the game of Go. I don't know much about it, but ways in which you can freeze out the opponent and things like that. This is the Cirque of the Towers in the Wind River Mountains in Wyoming, and it's actually not that hard to get here. If you're into backpacking, definitely go to this place sometime. All right, just briefly as an interlude, if you wanted to work with reinforcement learning yourself or play with it, one option is to use the Ray RLlib library, which is fairly easy to use. They have a nice command line tool, so you can like install it, and then, let's see, how do I do this build? Run these 3 commands to basically install stuff, and this is a TensorFlow example, even though TensorFlow is no longer sexy, I guess. To actually train a model, and it's actually training a small neural network. It actually turns out to be pretty trivial to solve. The example, I'll show you a little video of this, but basically it's a cart that goes back and forth, and there's a pole on it, and you're trying to keep it balanced. And the trick there is to know when to move left or right, how fast to move. But it's actually pretty easy to solve. And then there's a ton of different algorithms for how this process works. What you actually do during an episode is a little bit of the art here. This one happens to be using something called DQN, and I forget what that stands for. Deep Q network, that's what it is. And Q is a term of art in this business. We'll see how, there's another one called PPO that they use in ChatGPT. And then once you've trained the model, you can use this command RLlib evaluate, which is to actually run it and see what happens. And let's see what that looks like. It's not extremely exciting, but after about training 50 episodes or so, it does this, and it actually, can balance a cart. Okay. So as a tool, there's actually quite a few reinforcement learning libraries out there. This one is great because it is very performant. It has a rich set of libraries of reinforcement learning algorithms for people who are, working at that level of expertise. It's integrated with this. OpenAI has been really great in this business. They created something called GEM, which is really like an exercise environment, like that cart we just looked at. But they have things like robots, 2-legged robots that you can run and train and so forth. Integrates with the popular toolkits like TensorFlow and PyTorch and so forth. So check that out if you want and just play with it on your laptop. Okay, let's peel the onion a little bit about concepts in reinforcement learning that you might run into that become important. One of them is the idea of exploitation versus exploration. So when we watched that video, obviously they were running around not really doing anything terribly useful at first, but then eventually somebody stumbles onto something that seems to help, that seems to work. Either makes it easier for them to get to the guys that are trying to hide, or conversely, makes it easier for those folks to avoid being caught. And that would be a case where I've suddenly hit what seems like a good reward or a good strategy. Do I keep exploiting it, or do I actually want to explore the space further in order to find maybe better options that might be lurking out there, something that might actually improve the long-term cumulative reward that we talked about. And there's a whole bunch of ways this is adjusted. Now, curiously, when we talked about like playing the game of Go, where there's no reward until the very end, it's actually kind of tricky to decide, well, how much do I keep exploiting versus exploring? Because I'm not getting any feedback initially. And so this has become an area where there's been a lot of optimization, and even things like maybe at the beginning I'm going to explore a lot more and not trust very much the results I'm getting, but towards the end I'm probably converging on a good model for how I should exploit what I know. So that's called the exploration or exploitation versus exploration trade-off. The other interesting question is, what does make a good reward? So going back to the game of Go or any game, you could think about, well, certainly there's some states on the board, like intermediate states, that might be good to offer as either a negative or positive reward. So maybe I should be smarter about these incremental rewards and not just wait till the end. But the problem you can run into, though, is that you might end up over-optimizing for, I'm blanking on the terms at the moment, but basically instead of getting the global maximum reward, you sort of hit a plateau of something that's good, but not the optimal. So that is actually the challenge with rewards. Sometimes picking a kind of a dumb choice for rewards actually makes you do the right thing long term, rather than trying to encourage good behavior in incremental steps. Because you're going to play millions of these episodes anyway, so why not just keep trying everything? All right, so this is a subject. Offline reinforcement learning is one technique for addressing this challenge of, geez, it'd be great if I could train reinforcement learning to run my chemical plant, but I cannot just hook it up to the plant while it's completely stupid and just taking random actions, right? I don't want to blow up my city or whatever. So one of the ideas, though, is that because we're talking about something sequential and we're observing state at each level, well, we probably got all of these logs of data from the past, observations, metrics, whatever. Can we take those and treat them as like a tape, sort of like a Turing tape, if you will, and run them through the system, train a system to act optimally based on that the feedback from the past, and then hopefully, starting with a naive policy, actually develop something that's smart enough that I'd be willing to hook it up to my chemical plant. And so that's another way of approaching this problem. And you can even do things like generate fake data sometimes for this purpose. Now, one interesting difference now is that whatever actions my agent might want to take are going to have no effect, right? Because I'm just playing the tape from the past as opposed to something that's live. The other approach you could take to solving something like a chemical plant would be to write a very good simulator. There was a team, I think it was from New Zealand, who won the America's Cup, that big racing thing a few years ago, where they actually trained, used reinforcement learning and used RLlib to train how the rudder underneath the boat, the one that's actually doing the skimming on the water to get the rest of the boat out of the water. They actually trained how that worked with reinforcement learning to optimize their performance. The rules of the race are such that they could not actually have the model control the rudder. But apparently they had a guy who was had this thing running, the simulator, and he would just kind of manually do whatever the simulator was saying to do. And that was legal. That was legal. And they won the race that way. Okay, so this is an approach when you've got historical data to work with. All right, now let's talk about ChatGPT a little bit. And the concept here is reinforcement learning with human feedback. The two links here, the first one is a blog post that they published that was actually announced in ChatGPT, and they talked about this in some detail. And then the second post is from Hugging Face, where they go into more depth about variations on how people are using reinforcement learning with human feedback. And it's sort of based on this idea, which I took right out of the Hugging Face post. Wouldn't it be great if we use human feedback for generated text as a measure of performance to go even one step further and use that feedback as a loss to optimize the model? What loss means here, that's just kind of a technical term for loss would be like the measure of your error, how well you're doing, and then minimizing the loss is how you improve the quality of the model. So can we use humans to actually go a next step? And this is where the idea emerged of reinforcement learning from human feedback. If you were paying attention in yesterday morning's keynote, this should look very familiar because Alex put this picture up. This is from the ChatGPT blog post. I'm going to just take it to the next level and walk through their approach to using this technique to improve the performance of ChatGPT 3. And it basically became 3.5 after this process. So it starts with collecting useful data to create a supervised policy. Again, supervision is where I kind of know the answers in advance, and I'm using that to make the model work better for things that I already know what the answer should be. So the idea was you ask the thing, you give it some prompts, like explain like I'm a 5-year-old how reinforcement learning works, that kind of stuff. And you'll write a bunch of these, but then instead of just taking what the model gives you, you'll actually ask humans to write answers. Now already you're running into a potential problem where you have to be sure that the humans are going to do a good job. And of course we're all great and perfect at this kind of stuff, so really it's not a problem, but in fact you do have to be a little careful about it, right? So you have humans do the answers first, and then you take the model that you had and you continue to train a little bit more, and this is a process called fine-tuning with these answers to make the model even better. And what we're actually building is, remember I mentioned the policy is the thing that the agent is using to make decisions about what to do next? So we're actually treating this ChatGPT model as a policy for creating answers. So fine-tuning there's some interesting points here. Fine-tuning is pretty commonly used. Like, let's say that you work in the medical field and you want to actually make ChatGPT smarter about answering medical questions or understanding research papers or doctor's reports in medicine. One way to do this is to add that extra data from these sources and keep training the model with the additional data. The challenge here, this is getting into an area that's of sort of current research. The challenge is if it's already taking like thousands of GPUs and months of time of compute time to train these models, even fine-tuning to add an extra little bit is adding a lot of enormous complexity and expense. So there's actually interesting techniques people are starting to use called prompt tuning, where they actually build a little model that basically tweaks the prompt in a way that actually causes it to generate better answers and not actually touch the language model itself. So they're sort of like gaming the input in that way. I think Alex mentioned examples of another approach called prompt engineering, where you manually do things like feed it examples like, yeah, this is the kind of code I want, now give me a piece of code that does X or something like that. So that's another sort of variant on that theme. Anyway, that's kind of aside on some of the challenges right now with these large language models. Okay, next what we're going to do then is start sampling some prompts, and we're going to let it give us like 2 to 4 answers. And the reason we get different answers is because all of this is probabilistic. So if you ask ChatGPT the same thing over and over again, maybe in a separate session, so there's no chance that it's remembering your prior questions, you'll get different answers. Hopefully they're close, but they could be way off, and which is of course the challenge sometimes. But then you'll have a human label these answers like best to worst. And you'll use that to create a new model, which is called the reward model. So in other words, when we start doing reinforcement learning and we want to get rewards back, this is what will actually return a reward for whatever answer it was fed during that process. All right, now we're going to go back and optimize the language model. We've already fine-tuned it a little bit from the first step. And we're going to do some more. And in this case, they used an algorithm that OpenAI developed called proximal policy optimization. It doesn't really matter what it is so much. It happens to be very efficient and easy to code up, and it works in a parallel environment pretty well. So if you see PPO mentioned, that's what it's all about. All right, so we'll start by sampling prompts again. And we'll use this model, take the model that we had down in the left, bottom left, and we're now going to go through a supervised learning process, basically with reinforcement learning. So we'll ask our policy, again, the model, all right, here's the prompt, now give me an answer for so many cycles. So the policy now will give us an output like, all right, here's my explanation of reinforcement for a 5-year-old. We'll see what reward comes back like, I don't think that's so good, or actually that's a good answer, that kind of thing. And then we'll use that in a cycle to update the quality of the model using the same reinforcement algorithm or approach that I mentioned for all these other things like games. And that's basically how they improve the quality of the answers to be a little bit more of what people want to get rather than some made up text. All right, so that's kind of what they're doing. All right, let's talk about something that maybe is close to what some of you are doing in your day jobs. We don't all get to play games and so forth, but you might actually be working in systems that have to make recommendations or serve ads. So how is this useful? Well, one of the problems, I think we've all seen this, you buy a toilet brush or something like that on Amazon, and then all of a sudden you're getting ads repeatedly for toilet brushes or whatever, right? Like, how useful is that, The fact is your preferences have now changed because that need has been satisfied, hopefully just in time. Or, you're on Netflix and you happen to love action movies, so you've been watching a bunch of them in a row. Well, are you going to keep watching action movies, or maybe would you like to get a romance or something just to mix it up a little bit? So you might penalize recommending action movies as this person hopefully has more taste than just action movies, and as they start watching them. And there's all kinds of reasons your interests might change. Secular things like the weather is changing, summer to winter, the economy's going up or down. Maybe you want to buy cheaper stuff when the economy's not so great. And even like world affairs and so forth might affect your decisions. Again, reinforcement learning is great when we're tracking something that's changing, that's evolving. So can we apply it here? There is some drawbacks that I'll mention first before getting into a little bit more detail about the algorithm. But it doesn't scale quite to the large state space that some of the classic methods in this space can actually do. So if you think about like the Amazon catalog versus users in Amazon and the kind of big matrices involved in that, if you know anything about the classic methods for this approach, or Netflix and its giant user base and catalog, it's not going to necessarily scale as well up to those sizes. But what it is going to be good at is when you narrow down the options a little bit, both things this person's likely to be interested in and people who kind of fit in the same cohort, that's where this is useful. So it's often a case where you might start first with traditional methods to get an approximate answer, build cohorts like this of products or services and people, consumers of them, and then use reinforcement learning to train from there. The other thing they do is you don't really want to do this with customers. You don't want to throw a naive reinforcement learning model at customers, then you're starting to recommend stuff that's completely irrelevant to people. So you often start with simulators that try to simulate how people are actually interacting with your site. And then when it gets smarter, try to actually use it with real users. And this is actually a good case where you might use reinforcement or offline reinforcement learning to help with this, because you already have all this data about how they've interacted with your site in the past. And actually, when you read the papers and there's a list of references to what YouTube and Netflix have done for this in the extra slides. But one of the interesting questions is, how do you decide what the reward is in this case? It makes sense that there'd be some measure like human satisfaction or happiness, but these are really subjective things. So how do you define a reward function that represents the reward when you're doing this? And it could actually depend a lot on the category of stuff that we're talking about. Like toilet brushes are not something we all get really excited about, except when we need one, right? But movies are one of those things that probably elicit emotional responses more so than just I need to watch, the latest Star Wars movie, that kind of thing. So this is where some of the art comes in, picking rewards, is how do I decide what's actually going to represent the way users interact and will appreciate or not the recommendations I'm making. So anyway, here's one paper that YouTube put out. I think this is like 4 years ago. And they have this architecture diagram where they're using historical data that they know about viewer preferences, but they're using reinforcement learning to optimize how they're recommending videos based on how their preferences are evolving. I know that I tend to subscribe and unsubscribe to channels every now and then, so I really don't want recommendations for things I've decided that I want to see anymore. And so it's kind of interesting to watch this in practice, I guess. Also, in the extra slide, actually I think this is on the final slide, there's a nice tutorial that Anyscale, that's the company behind Ray and RLlib, they just came out with a new tutorial on reinforcement learning, and they have an example of some of the details about how to build a recommendation system that I think is worth going through if you're interested in this. Okay, so that's kind of it. And here's some links for further information, and I'd be happy to take your questions. Yeah.